Welcome back to the last and optional section of this entire module. I want to leave you with a few thoughts moving forward. Uh, you are here to learn or dive into the world of data science, and I would like to give you a few notes and maybe provide some tips and tricks for you to digest as you build your career. Most of the stuff I say here may sound abstract to you right now, but as you develop a career in data science, most of this stuff you may be looking back on and say, okay, this is what that meant. And I see the importance in having these concepts in mind every time I develop or I work on a data science project. So the first question we may ask is, are databases an efficient storage for data science projects? Because if you have had a prior exposure to data science projects, you may not have come across databases. Maybe most of the data you dealt with has already been formatted and structured and cleaned into, say, comma separated values or tab separated value documents like CSVs or even Excel spreadsheets. So why databases? Uh, this is not a simple yes or no, like almost everything uh, these days. So it depends on what you're looking for. There is a reason that we use databases. It's not like data is intentional data that was built for data science projects is intentionally stored in databases. In fact, you don't usually you gather data, but you don't construct data for uh, data science projects. Basically, you get the data and you work on cleaning it up, formatting it, making it available for your programming languages or for your data science projects. But databases historically have played a very, very big role in software engineering, and almost all the systems out there uh, today, including those that have been around for decades, rely on databases for storing data. And uh, no matter which way you cut it, data is still data. And there's a lot of rich information just sitting in databases that is waiting to be analyzed. Um, the data scientists really would like to get their hands on. So one way or the other, eventually at some point as a data scientist, you will have the need to connect to a database and import that data into your system. So they may not be efficient to work with directly as opposed to, for instance, reading data from a CSV using the very powerful uh, data science tools and libraries in Python and other programming languages. But nonetheless, they still hold a very, very rich data inside. So there is always the need to use, uh, at least to have the skills ready for you to use when the time comes to access databases. So this is one of the reasons that this module was included in this data science course. So, like I said before, tables are structured. Also, JSON is very structured, but um, a lot of the stuff that you hear today somehow does not mention stuff when we talk about data, mention stuff about databases or database tables. What you would probably hear a lot more often is about JSON data structures, which are basically the chosen format of communicating between different systems. Let's say if you have ever used any API for any of your projects before, if you have ever made a request to an API, what you're very likely to get is something that resembles a JSON format. In fact, almost all modern APIs provide their responses, and you're also able to query them using the JSON format. So JSON is a lot more popular way of communicating. And like I said, NoSQL databases store their data, at least some NoSQL databases store their data in a format that is very, very similar to JSON. And they're very easy. JSON, there's almost all programming languages have built-in functionality, if not third-party software that will help you easily handle JSON format data. Um, so that makes them very popular in terms of especially software development when it comes to communicating between softwares and also communicating between users and like front end and back end applications. So databases usually sit at the bottom tier of the software architecture. And as you go further up, there's the application on top, and then there's the place where your users communicate with your software. And that part of the communication usually uses JSON formats heavily. So it's not like you can say this one or the other. But when you talk about data science, you probably want to manipulate data if it's given to you in JSON format, if it's given to you in data stored in databases or a CSV file, an Excel spreadsheet. Data can come in many forms. And you, as the data scientist, do not choose uh, how your data uh, is stored, because you, as the data scientist, usually uh, look for data that is available out there, or at least say, as researchers run experiments that store data somewhere, um, and that data may not always be sorted in JSON format. So in many applications, databases are more efficient, especially if you're doing lots of reading and writing. But ultimately, you don't get to choose which format your data is, because there's a lot of hundreds of thousands of systems. They generate data in many different ways. Uh, the fact is, almost all the time, you have to have a pipeline where you take any of the data that you get and transform it into a format that your data science project understands. So, if my advice to you is, when you design and build your data science projects, make them try to make them more robust to changes in the formats of data. It's easier said than done, but in the long run, the more robust your pipeline is to changes in the format of your data that you're importing, the less work you have to do to adapt your data science pipelines to different sources of data. So the takeaway here is, be ready for all types of data formats, database tables and JSON definitely, and CSVs, spreadsheets, and who knows, like you may be dealing with image data or audio data. So um, there is always going to be a pipeline before your data gets into your actual processing of the data. There's usually going to be a pipeline which does transformations. So invest in a very robust transformation technique, so that you don't have to do the same thing over and over again as your data changes, and you can focus on the actual logic of doing the data science. Okay, so I have put it here as a third point, but we have touched upon it multiple times. Um, so we have data science. Uh, that term is relatively very new compared to uh, how long software has been around, but that doesn't mean that it's something that is completely different from software engineering. Um, as a matter of fact, you write code. Software engineers uh, design software, build software, and they write code. For your data science project, you write code too. So there must be something that you, as the data scientist, can basically adopt from software engineering practices that would help your data science project. So I want to say a few things about um, what you, as the data scientist, can borrow from the best practices out there for software engineering. The first one is testing. So um, we did something during the Python demo where we were making assertions. So that revolves around testing. So the biggest question is, let's say you build a data science uh, project where you take data from somewhere, transform it to whatever format you need, or you don't need to transform it. It's readily formatted in the structure that you want, and you build a predictive model with it. So there's a lot of things that happen through that process. So you have to write the code, import the data, and using your code, and then get a machine learning model, feed it the data, do the training, testing, and then you evaluate the performance. So just like what we saw in the Python notebook, you probably would have multiple lines of code uh, that do that for you. And then you get a very good performing model. You have done the testing. We have done the train test labels, and then you have done the validation. You did, let's say, you did cross validation. You did the train test split very well, and it is something that you can prove that you have done. Let's say you used a very popular library to do that, but you data science pipeline starts with the first code and it ends with the last code. In between training the predictive model and getting the results, and or even with the start, like you're importing a library and loading data uh, into your your environment, say your variables. There's a lot of things that are going on. So if someone asks you, okay, this looks like a good model, it's performing well, but how do you know it works? You have evaluated the model, so you know the model works. But whatever you did before, all those lines of code that you wrote, how do you know they're correct? Most of the time, especially in academic environments, the way we know software works is we run it and we see the results. That means it works. But in software engineering, that's not how we do testing. We write tests to actually make sure that our code runs. So what you do is, let's say you have um, a few lines of code that compute the Fibonacci series. Um, so you give them a number, and then they'll tell you this is the result. So let's say you have written the code that actually does that. So how do you test it? Basically, what you do is you give it a number, and you know you expect a result, and it gives you a result, and you compare those two results. So that's basically what we were doing when we were doing assertions in the demo earlier. So in software testing, this is basically what we do. We write a certain number of test cases. Usually, the best practices is before even you start writing any of your code, you write your tests. You have your tests ready. That way, you're not biased. So once you write the test, you've already seen. Once you write, you have written your program, your function, your data science pipeline. You know what it does. So you, as the person writing the tests, somehow are open to bias. So the best thing to do is before you start writing your code, you put together a set of test cases, which is called a test suite. So the expected result, and you run your like you have the input, the expected results. You give your input to your code once you have written it. You take the output of your code, compare it with the expected results. If the two are different, then that means your code is not working. So this is basically the most basic and uh, principal element of writing code and software engineering. Testing is something that you should never compromise on. So if it's a lot of work writing tests, but it pays. So the more you spend on testing, the less your code is open to errors, and you can say, I guarantee it works because here are the tests. So this is how you should also approach. This is how we approach, or at least how we should approach uh, software development. And you, as the data scientist, this is how you should also approach your data science projects. The next one is computational complexity. So every time you write code, especially when you're dealing with data, because data is in reality very big, especially these days. That's where the big data word term comes from, because data, it used to be maybe because we didn't have readily accessible data in the past, but as soon as computing storage power became cheap and readily accessible to many people, the amount of data we can get our hands on increased like exponentially. So there's a lot of data out there. So when you're dealing with big data, your code may perform very well for a very small sample of data, but you need to make sure that your code is scalable too when it comes to ingesting large amounts of data. So let's say in my Python notebook earlier, I tried to load the entire employees table. My computer, I don't even need any powerful machine. My computer can easily do that because it's only 300,000 employees, and I can probably load that into memory without any any problems. Now, let's say I built a software tool that does exactly that, and I want to use it tomorrow, not on the employees' data, but on some large database with, say, 12 billion rows. If I do not uh, design taking into account time and space complexities, basically I will run out of memory as soon as I try to load that kind of information into memory, because that's a lot of data and there's always going to be a constraint. So my advice to you is, when you write code, especially when you're dealing with memory, take into account how much data you're trying to load. Like, uh, do simple calculations. If I change the project tomorrow and got more data, how much space how much more space am I going to need? Is my space constant, or is it going to increase with the with more data that I have? What if I try to load not the entire data, but in terms of partitions, one at a time? That sounds like a good solution. In fact, that's how many uh, data science and machine learning libraries are designed to do. you do not load an entire data, because there's way too much data than there is enough memory uh, and storage. So we have to take into account these constraints. So this is good practice that I would recommend that you follow as you progress through your data science career. So that's the third point, what I just mentioned. So only read the amount of data that you need. Do not load everything. Eventually that will break your system. So you have to be very conservative, or at least be as conservative as you can when you're loading data into memory and when you're making calculations. Let's say you're multiplying matrices. Let's say you're doing a computer vision project where you have to deal with images, and those are usually represented as matrices. So you may be okay if you're looking at very, very small uh, images and you're only doing multiplication of, say, 100 by 100 matrix with something else. Um, but what if you're dealing with a very, very high quality image? That's going to be very difficult. So you have to take into account when you're designing your projects, if you can stay as conservative as you can, uh, and design your project to scale towards large scale projects, then that's a recipe for a very highly maintainable and efficient data science project. So always think about uh, being conservative with your code when 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 you're designing the memory and time and space requirements of your code. So the next one is, how can you automate your data science project? What we saw earlier with the Python notebook was I was executing uh, each line one at a time so I could show you what was going to happen. Let's say you take that data in, and again, going back to prediction models, you uh, want to train a model. When you do that, if you're doing it manually, then you would have to sit in front of the computer and execute each line of code and get the model started training, which could take a few minutes depending on the data and the complexity of the model, to a few hours or even days. Um, do you want to sit in front of that computer the whole time? That also brings us to the final point. What if during the model execution some error occurs? Are you going to start again? All the hours that you spent getting this model running, are you going to start from scratch, throw that away? If there is no other way, okay, but usually there are ways. So you should always design your data science projects to launch them and make them self-sustaining throughout their life cycle. That way you can just fire them and forget them and find out when they're done. And if there is going to be an error, try to make sure that you handle the errors so that they don't break your pipeline. Because there's always going to be an error at some point. Say when you're dealing with data that is like millions of lines or rows of data. Maybe there's a null entry in your data. So if there is a null, if you get data that you do not expect, because data is not perfect. It was collected by people, it was collected using software for decades and decades. Software has bugs which trickles into your data. So there is no 100% perfect data. But you don't want that, you don't want that to have a major impact on your pipelines. So what you need to do is try to account for the fact that there probably is going to be an error when you're parsing through millions of rows of data. So what happens if I get something that I did not expect? Do I continue? Was it a critical error? Can I skip it? So these are decisions that you need to make. That way, if an error occurs, your data science pipeline still is able to finish processing and get to the point where you need it to. So I know this is a lot, and most of it sounds like very vague, but I promise, like I say, as you progress through data science, and once you uh, have practiced and probably gone through some basic data science projects, you will eventually understand and hopefully appreciate these pointers. So thank you for staying on for this optional video and for being patient while I rambled for quite some time now about these intersections between data science and software engineering. Um, I hope at some point this will be helpful in your career, and congratulations once again for completing this module.